Now, a motor is an electromechanical device that converts electrical energy into mechanical energy. And motors in industry makes up 70% of the electrical load. Now the question is, why is a motor rated in kilowatt horsepower instead of kVA, like we're rating the transformer? And the reason for that is the motor has got a fixed power factor. So it's a defined power factor, and the rating has been mentioned in kilowatt on the motor nameplate. And that's why they are rated, the motor are rated in kilowatt instead of kVA. In addition to that, a motor is a device that converts electrical power into mechanical power. So the load is not electrical but mechanical, that's the motor's output. And we take into account only the active power, which is now converted into this mechanical load. So that's why for a motor it's specified in watt and not VA. Now just a bit of a review how it operates inside the motor. Firstly, it uses Faraday's law, which states that a time-varying flux will cause an induced electromotive force, or EMF, according to this formula. So the picture on the right-hand side, if you have a current flowing in a conductor, there will be a magnetic field. And you can create a path for that magnetic field with some magnetic material. Then we have Lenz's law that states that the current that flow in the coil in such a way that the magnetic flux generated by that current would oppose the increasing flux. So we'll get back to that when we look at the operation of an induction motor. So it actually wants to reduce that increasing flux, and that's why it starts to rotate when we look at an induction motor. Now if we have a conductor and that carries current in a magnetic field, then a mechanical force is exerted on that, and that force on the conductor is given by the formula F is equal to BLI. So So B is the magnetic field, L is the length, and I is the current. It depends on that current. And that's basically the principle that happens inside a DC motor. So we have the commutator, and we have current flowing in the windings of the armature, the rotating part, and we have on the stator part, not rotating part, we have a magnetic field, DC field that we apply. So that creates a magnetic field. And that because of that, we have a certain force that's been exerted on that conductor. Welcome, Travis. Now, Fleming's left-hand rule, not a problem, gives us the relationship between the direction of current, the direction of the field. So there's the magnetic field. We have the current flowing through it. With that and the left-hand rule, we can determine what is the force exerted on that. So if we put all of that together, we can then decide with that left-hand rule what is the force. And you can see the force in this drawing is downwards on that conductor which carries current. So if the conductor on the rotor has got a radius of R, then the torque produced now because of that is given by this formula, F times R. We've already defined F, so we can just replace that. And if we have a coil with two sides, that electromagnetic torque will be double. And power is then the torque times omega R, which is then 2 pi F. So the electromotive force is induced enough to overcome the drop of volts in the resistance of the winding. So as current flows through there, there will be drop because of the resistance. So your EMF will be enough to overcome that and supply the load at the required voltage. So the EMF will be low if there is no load. As the load increases, that EMF will also increase. And the electromagnetic torque produced by this current carrying conductors is counter torque opposing the rotation. But there you can see we have now two windings. It means the current in each of them flow in opposite direction. So the force on those two windings is in the opposite direction, and you can see that actually causes rotation. So that's in simple what happens in a DC motor. So as you can see, our machines utilize the concept of electromagnetism. So in case of rotating electrical machinery, we have the magnetic field that interacts with either an electric field or a mechanical force to produce the other. Now, a mechanical force is where we have a generator. In a motor, we will have electric field. So if we then go back to the motor, we have a magnetic field and the electric field that interacts with each other, and that produces then the mechanical force. So this is then known as a machine, and the same machine can convert electrical power to mechanical power or the opposite. So even if it's an induction motor, there's modes in which it can operate that it actually will produce power and not use power from the supply side. So a motor goes from takes electrical power, converts it into mechanical power, and with a generator is just the opposite. So the requirements of motor and generator usually dictates different designs, and different types of machines in industry are principally synchronous machines and asynchronous machines, which is one of them is the induction motor. And both of them we get in single and three phase. Single phase is limited to low power up to a certain kilowatt. So in industry we would mostly use three phase machines. And for this module further on, we will then focus more on three phase machine than single phase machines. For single phase machines has got a little bit of a different design.